visual effects. So let's go ahead and take a look at TP. TP inside Max, we're in Max 2016. We go here onto the Create tab, Geometry, create a particle system, create a thinking, ask for my license address, and we go ahead and we click out here once to create one TP, and then we right click. For those of you who know TP already, this is going to be the very slow part of the video. We're just going to cover some basics about how TP works and things to watch out for. And we'll talk about how data flows, the categories of operators are, some of the pitfalls, things to watch out for. We'll look at how to debug systems, and then we're going to go ahead and build a couple basic systems. So to access the TP UI, we select our TP. Let's see, it's called Thinking 001. Go to the Modify panel, and then click on Properties. Actually, let's click on About first, because we want to see which version of TP are we using. This is 6.4.0.884. And so this is the most recent public release. Let's go ahead and click on Properties. So here, I'm going to adjust my UI. Make this so I can see. Oh, my monitor is a little bit smaller than normal, so let's do this. I'm going to do a little rearranging. And let's pull this over here. We need some space to work with. Okay. So those of you who have watched my videos, the free videos, there are actually 27 hours of videos on Thinking Particles on Vimeo and YouTube. And there's so many great tutorials by so many different artists. So many people have put them out there covering different areas. It's really a community-driven experience, and so many great things to learn from so many people. But if we go too fast, or you want to explore other areas, definitely check out those other videos. So here, let's go ahead and talk about this UI. Up in the upper left area under Master System, this, where it says All, is the group area. Groups are the way that we organize particles. We organize them. Let's go ahead and create a group. Well, we already have the All group, but we don't really want to use the All. You can, but believe me, you will want to create specific groups. We'll give it a click to rename it. We'll call this one Test. Now this is the group area. These buttons are for managing, creating, and removing groups. We can reorder the groups with the up and the down. Right below that is the master dynamic. And this is where we create the rules, or also called dynamic sets. And in here, these are the containers in this space, which is the work area, where we will create pieces of logic that work together and allows data to flow in order to make certain things happen. Okay, so group area, dynamic sets, work area, and over here on the far right, this is the properties area. And this will change based on whatever you have selected. You see, if we select the group test, we get properties for this particular group. We'll go ahead and change the color. And now, see, we click all. All is still white. Test is red. All of these properties here are explained both in the help manual as well as many videos online. The most important ones, in my opinion, are right up here at the top. We can control how exactly they are displayed, or if they should use the global settings that are on the master dynamic here. We can say if we should show the mesh for this particle group, if it has a mesh assigned, as well as whether this particle group should render, and whether it should cache or not. And this is very handy because you will have complex systems with many groups that are just helper particles. They are just there to achieve some utility function. And so we probably will not want those to cache. But in our case, for right now, let's cache these. And let's create a simple emission system. This will be our very first super basic system. And what we're going to do, and I'm going to teach you the first thing you should know about thinking particles is how to stay organized. To stay organized, you should always try to think one step ahead. What we build, we might want to use again. So try to always think ahead. So here, we have the master dynamic, which is the main controls for the entire system. And under the master dynamic are all the smaller rules that tell the particles what to do. We always want to start with one dynamic set that will contain our system. You can create systems that have multiple dynamic sets on the same level, but believe me, sooner or later you will want to save this. And the easiest way to organize these, and I'm just clicking and dragging these onto this. You see this arrow, black arrow, says it's going inside. If we start with one dynamic set for my system, then it will be very easy to save this specific system. Can also, I'm going to select all these dynamic sets in the work area, right click to access this menu, and we'll just say remove. We're going to start with a single dynamic set in this system. And actually, I know that many of you overseas, and a certain part of our audience is students. And so I want to give you the basics, but we also have many people watching who are probably working professionals. And so I would like to give all of you as much information as I can. For the beginners, this will mean that I will be going too fast and covering things that are too advanced. Maybe too advanced. And for the working professionals, I will sometimes be going too slow. But I will try to throw in some good tips to make it worth your time. Let's take a look at how I always create my systems. I start with a system because eventually I will give the system a name. Maybe it's a mission system. Maybe it's fire, smoke, whatever. Then we have the first dynamic set. But the first dynamic set, for me, is really the dynamic set that will be my first cache. So we call this cache 1. As we develop the system more and more, we will nest this cache inside another cache to cache another. And what I mean is, eventually, we'll have a cache 2 who will contain cache 1. Let's go ahead and leave it like this. Let's take a look at the groups. Just like we have a system dynamic set, we'll also have a group called system. And there's a very specific reason for this that the advanced users will understand, and the new users will want to know before they begin any complex projects. And that is because groups in Thinking Particles, let's go ahead and make a couple groups here. Let's call this red, call this blue. So groups in Thinking Particles, as well as dynamic sets, are organized in a hierarchy. Red and blue are included and are part of system. If I create a rule that affects system, both red and blue will also be affected. And there's something more complex, there's something in TP called data channels. And data channels are extremely powerful. Data channels are a way for us to bake information, extra information, into our cache that we can access later. And what I will do here is I will create a data channel, a very common data channel we use in production. I'm going to call it my size. This is the name field. This drop-down represents the data type. This is the float, meaning 0 through 1 with decimal points, or I'm sorry, not 0 through 1, but 0 through negative infinity to positive infinity, almost. Let's go ahead and add this float. So now we see we have a channel 0 with a name called my size, and its type is float. And we'll take a look at how we'll use that here in just a minute. But the reason I organize my groups under a common system particle group is so that I can store all my data channels in one place for this system. You see when I click on red, there's this little caret and then a my size. This tells me that this group red has a data channel called my size that is inherited from a parent. In this case, it's from system. The reason we organize groups under a common parent group and use data channels like this is because if I've selected blue, and if I add a data channel called test, you can see that blue now has its own data channel 1. Red does not have this. If I select all, which has no data channels, and I type in test2 and add a data channel. Well, for all, it's channel 0. If I select system, I have an inherited data channel, and then I have what used to be channel 0 is now channel 1. So the numbers will get all confused. Not good, believe me. I have seen so many artists get confused in production using data channels in the wrong place. So my recommendation is create one group for your system, not all. One group, and put all your data channels on this group. So every particle underneath this has the same set and the same numbers of channels. So let's get into it. Here we have cache 1. Let's create some particles. Oh look, a new version of GreenShot. Alright, so inside cache 1 we will create a dynamic set. We'll call this birth. Here you see we have birth. We can roll this up to make it small or expand it. And inside birth I'm going to right click and I get this menu. This menu allows me to access the existing particle groups that are up here. It also allows me to access different categories of, we'll call them operators in TP, just a general term. There are different types of operators. There are conditions, there are regular operators, and there are helpers. This category is called black boxes, and these are special because these are things, pieces of logic that we have created previously, and we save them, and so we build a library of pre-made items that we can just drop in at any time. And this allows us to make something once and build upon it without having to recreate it every time, which can be very time consuming. If we create an entire destruction system, we definitely do not want to recreate that. We can save the system dynamic set down here. We can save this somewhere, and then we can, at any time, we can just go to black boxes and systems and say load a system. You can see how many different systems we have. We have destruction systems, we have systems for tracking other particles or other data, all different types. And this is also where being organized is very, very important. You want maybe once a year go through your black boxes and just make sure that you only have the ones that you really want to keep. Okay, so let's go ahead and create some particles. We're going to go to the operators category. Actually, let me just back up real quick. These categories do different things, and you can see that the conditions right now only has one subcategory, standard. Operators has multiple subcategories. Helpers has multiple subcategories. So these are all different types. They do different things. As you learn thinking particles, it's very important to understand what each one of these does. For example, under conditions, standard conditions, we drop an always true. Always true has no parameters, but it has an output. And when we put our mouse over the output, we see that it has both a name down below, which I can't move my mouse to, and also in parentheses a type, which is bool, which is true or false. And of course, always true always sends out a true signal. And we can click on these and drag them to make connections. So let's go ahead and we'll try just a simple example. So we'll right click, and under operators we have a category called generator, and generators make particles. Here we go into position born. This operator creates particles at a position. Right now it has a whole bunch of it has all these parameters that are pre-built, and here we have group. So which group is it going to put those particles into? Let's put them into the red group. And just to be sure, let's click on red, change its color to red, and we'll click on blue, change its color to blue. If that is the only thing we change on this generator and we begin to scrub, we can see some particles being created. This is, it creates a count of 25. Something very important is up in the title bar of TP shows important information. The name of the TP system, how many total particles, how many particles are in this branch, and how many in selected. And branch and selected mean when I click on a group, how many are in this branch? Everything on this selected and all of its children. And selected, of course, is this specific group selection. Here we have this and this. Alright, so let's go ahead and look at how we can modify this. We could modify these values in the rollout, and this will give us some different behavior right away. You can see our speed is different. We can select red and tell them to display as drops. And you notice that this does not change. This is because there are two parts that control how particles are displayed. There is the group itself, and there's also the master dynamic. And the master dynamic controls many settings in Thinking Particles. It controls, you can see we have an override for the viewport display. Right now, force this setting means display as ticks and show the mesh. We turn this off. This field here and show mesh area, these are what's called global settings. So if a group is set to global, it will use whatever the master dynamic's telling it to. But here we have red displaying as drops. Let's go ahead and we'll go ahead and make this a little more interesting. Let's change this to a particle rate, set this to 200, and see what happens. So now we get a lot more particles. Now let's go ahead and start to see how we can combine pieces of logic in TP to modify this. And all these, so this generator, position born, you can see it has something on the left-hand side, and it also has things on the right-hand side. There's this green circle called inputs, and another green circle on the right side called outputs. Data flows into this generator, and other data flows out. Right now, these exposed inputs are on, particle, and position, and the exposed outputs are particle, frame counter, animation counter. Each of these has a specific meaning, and there are many different operators in TP, each with different inputs and outputs. This is just part of learning TP. But what we can do is we can click on the inputs and get a menu. These are all the available options that we can create inputs for in TP. Let's go ahead and put direction. And let's also go ahead and expose speed. So what we're going to do is we're going to tell these particles to go in a certain direction. To do that, you see we have direction here, and in parentheses you see it is of type direction. Now a direction in TP is a normalized vector or unit vector. In order to do that, we need a helper under math called point 3. Point 3 has three components here, x, y, and z, and some other functions. In our case, we want it to set to added. And what this does is it allows us to define a vector. In this case, we'll just use x1. So x1 goes off to the right, like this. Let's connect that into, well, you can't take the x value. You can see that TP shows us where it can connect by highlighting those inputs. Now, I don't really want speed of 1, so let's take our vector, which has a vector output type, and you can see that it allows us to connect to position, speed, and direction. Let's go into direction. So what happens is TP thinks I have a point 3, a vector. It's pointing in the x direction. Take that direction, feed it into position born. Position born uses this incoming direction, this incoming vector, and it will send those particles off to the right. Now it also has some variation in it because this operator itself has direction variation. Now, as you begin with thinking particles, it's very useful to go to the master dynamic and turn off edit on the fly. This button is both your best friend and one of your biggest enemies. If you turn this button on, you can make any kind of change in TP and nothing will happen until you move the time slider. If you turn this off and then you back up one frame, now anything we change will be recalculated from the beginning to the current frame. Just like this. So, edit on the fly is good when things are not very complex, but when you start to build a big destruction system, it will become very, very painful because anything you change will take time to update to your current frame. Alright, so let's go ahead and also let's create a second rule for this. We have some particles now, and let's say our goal is to have them start to move upward after they reach a certain age. Right now you can see in our timeline maybe around frame 30. Let's check their array. Well, they only live to be 30, so let's change their lifespan to 50. This will make them live longer. Now they reach further. And what we will do is create a second rule under cache 1. And here we will say move up. And we're going to affect the red group because that is the group we put position born into. And we'll say red. And what we want to do now is there's a very big difference here. these generators have a Born particle output, and this is very important to understand. Born particle, if we connect something here, like let's say we create a force. So force, and this is also important, you see it's highlighted, the particle. It tells us this is required. Connect that, and now it is fulfilled, and it will work. If we set this force, say, to -50, and it's set to direct, what will happen is at birth, and only at birth, they will get force. Let's go ahead and right click and say copy. Go to move up and paste. And now we connect this. And you see how we do this. We can click and drag this output to this input. And we hold shift and we can click on this to disconnect. Or we can click from this input and connect to this output. And our rule is called move up, but this will actually move us down. So there you can see this. Let's go ahead and move it up then. And what happens is the particle at birth gets some force applied, but only for a moment, only when it's born. When it gets into this next rule, it says, I want red particles to apply force going up 34 units, or 34 strength. It's a direct force. But apply this every frame, every sample. Samples are an important concept in TP because this controls how many times per frame change does TP evaluate. Right now here there's so many different parameters on Master Dynamic. It takes a little while to get used to them. But here under Viewport Render Subsampling controls how many times does TP sample per frame. We could say per frame, per half frame, or we can set the number of samples per second. Okay, so another pro tip. Let's go into the max time configuration. We should be on films for film work. If you're working in NTSC, set this. For film work, it's 24 frames per second. Let's go ahead and make this 10 seconds long. And go back to the Master Dynamic. So, pro tip for you, always set your samples per second to a multiple of your time configuration. So if I'm using 24 frames per second, whatever I set here should be divisible by 24. So I could do 24, 48, 96, 120, onward. 240, 480, and the maximum number you can do in 3ds Max is 4,800. Okay, I know this is going a little bit slow, and some of you may have some questions here soon. We're going to go ahead and add a couple more rules. We'll cache this, and then look at how we can modify that data after the cache, and then I think maybe we will go ahead and start to take some questions. So here we have our force pushing us. Okay, so now you see things start to are slow to calculate because 4,800 samples per second is quite a few. Let's go ahead and do per half frame. So as we scrub, okay, we can see them flow upward. Let's make this a little more interesting. Let's say, and at this point I'm going to turn edit on the fly back on because I want TP to stop or to not calculate every time I change something. And remember, anytime you change this, edit on the fly, back up one frame. Okay, back to this. So we're going to make this rule say, when my age is over 10, go ahead and apply the force up. To do that, we need to detect my age. For this, we use a condition called threshold. You could use particle age. Particle age, I think, is not as easy as threshold. Threshold just wants to know, in this case, am I over 1 or am I under 0? Or if we turn on inside, am I inside 0 and 1? For our case, what we want is if my age is over 10. Set this to 10, turn off inside, leave that, threshold 2. We'll connect our age to threshold's value, and threshold will test the incoming value and see, am I over 10, am I under 0, or am I inside that? Turn that off. And whatever the case, it will output a Boolean. Let's go ahead and expose one of the inputs for force. Let's expose on and connect threshold's Boolean to forces on. What this means is when each red particle, it takes the age, and if the age is over 10, it will output a true, and then this force will be applied. So now you can see they go a little bit further. To make this more apparent, let's change the speed variation to 0. So now they curve way up like this. Let's also reduce the direction variation. Alright, so now we have a nice stream there. This is all good. Let's make it more interesting. Let's say, as my age gets older, apply more force. So to do this, we're going to use one of the very nice new features in TP. Under Helpers, Standard, it's called Value to Value. We take the age into the value, and this value you see is required. And now it's fulfilled. And what this does is it interpolates the incoming value between the two input values, this min and max, and it outputs a value between these two values. Now the input value is evaluated over the width, the x-axis. The output outputs based on the y-axis. In this case, the way it is right now, as my age goes from 0 to 1, meaning 0 starts here on 0 on the x and goes to 1 on the x. So as my age goes from 0 to 1, I'm going to output the min value, which is the bottom of the y-axis, to the maximum of the y-axis. It'll output from 0 to 1. Now that's pretty boring. So let's go ahead and make it more interesting. Let's say, as my age goes from, say, 10 to 50, go ahead and make the output, and remember this is going to be our force strength, let's make it from 0 to 100. So let's take this and connect it to strength. And now what we also want to do is we want to disconnect this threshold. We are dynamically controlling the amount of force based on my age. We can also even disable this condition. Something very important I want to mention is if this threshold is connected to an operator and you disable it, nothing will happen. This is because if you disable this operator, the value coming into this force is undefined. And an undefined value will usually prevent this from working. So let's go ahead and hold Shift and just left click on. Let's go ahead and scrub this again. So now you can see my particles going up here. We have lots of time frame range, so let's change our lifespan to 240. And we'll see what happens. I'm going to get way out here. So now, yes, you can see the force really gets extreme. Now let me show you something that'll help you visualize this. New in TP is something called viewport color, where we can connect this to the particle who we want to affect. Right now this scale is set from black to white. That's not exactly the colors that will show up very well for us. So let's set it from green, like it's green at birth, and red, like it's, or maybe a dark red, as it's going to approaching its death. So birth to death. Now what we'll do is say, let's take this value to value, and notice that our viewport color has a min value of 0 to define this left axis, and a max value of 100 to define this right side. Well, as it happens, this value to value outputs 0 to 100, which matches this, so we don't have to convert this. In some cases you will, but we can go ahead and just pipe this right in. And what we'll see now is they start off, you can see this green, and as they approach here, they begin to change color, until finally they reach, wow, they go and get way up there. Well, actually it only interpolates between age 10 and 50. Okay, so again, let's make this a little more interesting. Let's say let's start to change the direction as well. Let's do another one. Let's add a second value to value. This time where my age goes from, say, 50 to 100, we're going to create a second force using this as our strength interpolation. So from 50 to 100, I go from 0 to 100 as well. But this time we're going to change the direction of this force. It's set to direct, which means that whatever the vector is, or this raw value, will be applied to the particle. You see we have a direction input, but nothing connected. If this strength is positive, it means it will go up. Negative is like gravity and goes down. What we will do is create another vector. Under math.3, connect our vector to direction. And this time let's have it go negative x. So they will go up from age 10 to 50, and then from age 50 to 100, this force will grow from 0 to 100 and be applied in the -1 direction. Yep, and you start to see them curve there. Let's actually add some -z to this. Bring it back down. Not quite enough. So what I think we should do is increase this force. So now we get much more extreme values. All right, this is just a very small aspect of TP. There are so many operators and so many things you can do. There are an incredible amount of approaches to visual effects. What we're going to do now is we'll go ahead and jump into adding shapes to these, as well as caching this system, and and then we'll show how this data channel can be modified after the cache. Let's do this. Our maximum age right now we're affecting is up to 100. So let's go ahead and set these to only live to be 100, I'll say 120. Something very important about thinking particles is when particles are born is a really good time to assign both a shape. So geom instance if you want to use a shape object from the scene, or you can use standard shape. There's also the very powerful new implicit shape for dynamic liquids, kind of like frost. But for our case, we'll go ahead and we will pick a standard shape. We'll use a cube. Render instance means that we can save on cache size because each mesh shape will be the same. And our position born gives us a size value by default, but let's go ahead and modify our size by assign, and again this is under operators standard. These are just the standards of the very basic properties of particles and basic things that affect particles. So let's affect size and set my size to be 10. Okay, now you can see that we have boxes. Let's go ahead and also give these boxes some unique alignment. This is also under operator standard alignment. So you can think of these things, operators are really like things that affect particles. Either their shape, behavior, or certain properties about the particles. Alignment has a whole bunch of properties. One of the main one right now is random. So as they come out, you can see now they are aligned randomly. And this is nice. We like this. Let's go ahead then and I mentioned data channels. Data channels are a very powerful way to store data inside a cache, as well as you can use it on the fly from rule to rule. What we're going to do is I'm double clicking these to make these small so they're compact. What we'll do is we'll say on move up, hold Alt and right click on this threshold to remove it. I want to store my particle size at birth. Now there's two different ways to do this. I could right click here and access a helper where I access and read particle data. And it's very important to know that the helper version of particle data will read particle data. And if we right click and say operator standard particle data, this is different. This allows us to set particle data. I know this. Let's go ahead and look at a very basic concept. You right click on this and there's a menu for affecting this operator. We can say visible all, and this shows us that there are a whole bunch of inputs on the operator version of particle data, whereas the helper version of particle data, if we say visible all, it has a particle input and then a lot of outputs. So if we want to affect and set something for the particle, we can do it with the operator. And if we want to read data about this particle, we use the helper particle data. In our case right now, we want to use the helper particle data, and this will allow us to say, now this is a good time to bring up an important part of TP, which is the evaluation order. So TP evaluates from the top down all the way through these. And then, data you can see flows from outputs to inputs to more outputs to more inputs. So it has kind of two directions of flow, top to bottom kind of left to right. So a very important thing in thinking particles is when is data available. In this rule, we have position born is the top operator. This means it is evaluated first. Now, thinking of particles is very smart. It can solve most problems without having to worry about the order. But there are certain cases where you definitely need to watch the order. One of them is this case. Here we have the size operator setting the size, and down below it we have the particle data where we can read the size. And remember, our goal here is to set the size into my data channel. So let's go ahead and create that data channel. It's under Operator Standard Data Channel. And now data channel has these different data types. This data channel happens to be a float, so we'll expose that. We'll connect this to my size. Double click this. The data channel can set which number. And remember, this is where it can get confusing if you set data channels on different places. So always try to set your data channels on one location. So, so why this is important. The position born occurs here at the top. And then you see here we have size. Next we have particle data here, and then data channel here. And this will work properly. What this does is it evaluates from the top down. The particles are born. It actually reads this 0.3 beforehand. That's okay. We could put it up here to be perfect. The position born then applies force, applies standard shape, down this order. If we put size below the particle data, visually it will look like this, but TP doesn't really care about our visual arrangement. It only cares about the top-down order and where data flows in and out. So, one second. So, if size, we'll put this down here visually, if size is after this particle data, the position born generates its own size, feeds it to this particle data helper. That size comes out here and is stored in the data channel. And this size value is what will be stored in the size, not this one, because the particle data reads the data, stores the data, and then after that, a new size value is assigned. So this is where it's important to assign things in proper order. Let's go ahead and learn something very important about thinking particles for everyone. New users, experienced users, everyone who uses TP should know about on the master dynamic is the debug log window. If you click this, we get this window that appears. And this allows us to show data flowing through TP and see it here in this area. We'll go ahead and select, let's go ahead and select this particle data helper. And remember, it is above the size operator. Now let's go ahead and right click on this output and we get another menu. We can make it invisible, or we can click here and show size again. And you can see that it has this greater than symbol saying that it is connected. And if we right click and say write to debug, it gets highlighted. And just a fun note, if you go on the master dynamic and under schematic colors, you can set your own custom colors, as well as things like text and aliasing, grid, display properties. But good pro tip for you, if you want to go fast, the only one you need is bended wire. Because on big systems, those other display properties will slow you down. So let's see what debug shows us for our particle size. In order to see this easier, I'm going to switch the position born to pistol shot. It means only fire one particle. We'll go to the first frame, and we'll go forward. You can see my particle data size equals 1. This means position born generates a size value. We read that size value with particle data helper and store that into the data channel. And then we set the size value to 10. If we move this size above particle data, and so visually it will look like this. Now, instead of being 1, which is generated by position born, the particle comes out, these properties are set, size gets set here, actually here, then particle data reads the current size of that particle and stores it in data channel. So now we get size 10. Very important concept in thinking particles. Remember to order things top down so that data flows logically. This is one of the biggest problems when debugging systems for beginners as well as some experienced users. Happens to anybody. Okay, let's switch our particles back to a rate. Our debug keeps firing. We don't need that. Let's go ahead and turn debug off. Let's go ahead and do a little scrub. Okay. So remember, we set the size first, then we store that in the data channel. Now I told you there's 2 different ways to do this. You can do it at particle birth, or I'm gonna select this data channel, right click and say copy, or I can right click and disable this, come into this next rule, add another condition called particle age. Particle age defaults to born. So if we connect particle here, this will fire true when the particle is born. And when this particle is born, I'm going to right click and paste that data channel. I can, of course I want to read a data channel for this particle. I expose the on for this data channel. So this is when I am born. I send out a true only once at birth. And this will have the data channel store that value just one time. And then I could expose the size of my particles, feed that into the data channel. And now if I clear the debug and write to debug log again, now you can see I'm getting those 10 values again. So there's 2 different ways to do it. I prefer to do everything at particle birth as much as possible. You can do it later. There's certain situations where you'll want to do a bunch of calculation, and then at the very end you can write all your data to data channels. Really just depends where you need the data in time. Okay, so let's take a look at how this approach for setting my size comes in handy. And believe me, we do this all the time on shot work on movies, because you want to create and put as much data into your cache as you think you will need later. So once you create that cache and you get the dynamics moving the way you want, You won't have to recache the whole thing if you just need to modify something simple. So here we are storing a data channel at the end of this. It stores our size. Let's turn off the debug. Another pro tip for you, all you guys, I'm sure you know this, is if your debug window's big, your Macs will actually run slower. If you want to debug fast, make it short. Okay. For our case, let's turn it off. So now, next big thing in thinking particles is once we have our particles doing something, let's go ahead and cache this, because this is being calculated every time we move, right? We get these particles moving around. This is all being calculated as we go. Let's cook this into a cache. So we select the dynamic set. Oops. And there's two places to click on a dynamic set. You can click on the name, or you can click on the icon. If you click on the name, oops, if you left click with a long click, it will rename. If you right click on this dynamic set, it will disable it. And disabled, nothing will happen. Nothing will happen inside this entire branch. And this is the beauty of thinking particles and its hierarchical organization. If you right click on the icon, you get a menu for caching. We can set the cache file name. We can also now write specific channels for TP. Very powerful. This helps reduce cache size, but be careful. Make sure you record the data you will need later. And surprisingly, DT factor is a big one. Now, we'll go ahead and create this cache. Let's say cache record. And because no cache name existed, it wants to know where and what to call it. It defaults to a frame cache, TPC. My favorite is still, this is per frame, so it will create one cache file per frame. We actually want TPS, TP simulation. This means one file that contains all data. Cache 1, it uses the name of the dynamic set. Let's go ahead and hit save. See, it calculates. Now our icon has changed. Now we are playing this cache. Let's go ahead and scrub. We can scrub forward and back super fast. The only delay is our hard drive. So this data is already set. If we try to modify size, make it 10 times bigger, they will still be the same size. If we right-click this play icon and say cache stop, the icon changes, and now our particles really are 10 times bigger. So let's put this back to 10. Let's go ahead and right-click and say cache play. And let's go ahead and scrub. This is our cache. And now let's look at why data channels and storing data in data channels comes in handy. Under cache 2, I'm going to create another dynamic set. I follow a standard naming convention where I call everything by a cache number, and then another dynamic set who has rules that affect an existing dynamic set that is cached. We call this cache 2 rules. If we had cache 3, we would have cache 3 rules. But here in cache 2 rules, we'll create a rule that says we want the red particles, and we're going to expose their data channel for size. And I want to modify that size by setting a new size. Remember, that's under Operators, Standard. Connect here. Now, I could leave it like this, and of course it will affect the size. But if we had very specific size objects, and we just want to multiply those sizes up or down, this method is preferred. We'll add a helper under Math called float, which is just a number value. It has some other options. We're going to go ahead and set this to 3, and we will set this to multiply. And what this means is whatever value comes in to float will get multiplied by 3 and sent out. Take my size that's in the data channel, and remember this is stored in the cache. Go ahead and put it out back into size. So now my red particles, we take their cached size, multiply it, and set the new value. And now you see they are quite big. And so this is how we can modify data after it's been cached. And believe me, in production shots, this will save your life, because if you remember and you store data in the data channel that you need later, it allows you the flexibility to keep that existing cache and all the dynamics that happened, and then modify specific parts, usually while keeping the same motion. Now, Thinking Particles is a very powerful and very complex system. It's very mature and has many different operators available. The most exciting are things like fragment and volume breaker, shape collision, bullet physics. And unfortunately, we don't have time to go through all of these. I do recommend that you go to the Vimeo channels or the YouTube channels. Like I said, there are so many good tutorials by so many different people about how to learn about these things and how to build systems. So this is really just the introduction. This is, the things that we have done with Thinking Particles, different companies on movies. And this is really just an overview of the basics. And thank you very much for being here tonight. It's been a pleasure for me to share my experience and just a very small introduction to the power of Thinking Particles. So we have another question. Can the latest TP viscoelastic solver handle magma type visual effects? I am very happy to say it definitely can. The new viscoelastic solver in Thinking Particles is very powerful, very flexible, and many of the new tools allow us to perform basically shading control of the mesh, implicit surface. Follow-up for that question is, as the magma turns into a solid, how can one handle the coloring of the mesh? And to be honest, this is a good question. I know it can be done. I've seen it done. I haven't done it in a while. I believe it's here under the implicit shape. Or let's also take a look under our fluids, which is under flow. Do I have edit on the fly turned off? Oh, there we go. So here's the viscoelastic portion of the solver. However, I believe that what you want is under the implicit shape. I could be wrong. I believe Edwin Braun and Cebas have videos out there. If not, you might want to contact Joe Gunn or Eloy Andalus-Fulla. I know they've both been working with that. Let's see, I think you will want to modify here under their data to mapping channel on implicit shape. We've got color for a mapping ID. So, and these numbers here, like UVW, you see -1, you see color, -1. These refer to which data channel to read from for this particle coming in. So you would assign, a data channel for, call it mesh color, add this to my particle, expose my mesh color here. Now, note that our data channel is channel number 1, and so for color we would set this to 1, and mapping IDs, I believe, will refer to I could be wrong, but they are going to refer to which map channel to use for this particular color. So this will be data channel number 1, and we'll point to UV mapping channel number 2. Yeah, the implicit shape and flow and smoke, new in Thinking Particles 6, have added new features that really enable some new creative possibilities. Cebas is dedicated to implementing new features and pushing the limit. They take a lot of feedback from users in order to, make the software more capable and more fun to use, deliver more artistic results, and back to giving users more flexibility. Yeah, it's really incredible with Thinking Particles. It's kind of like being on a frontier where there's so much unexplored territory, so many creative ways to combine things. And not just that, but using Thinking Particles in conjunction with other plugins, the particle skinner that's part of pFlow in 3ds Max. Particle skinner allows you to make tearing meshes. I'm hoping that we can integrate that into TP at some point. There's also, so many other new excellent features in TP6, like the Alembic export. So if you want to export groups to Alembic, in this case we could export the system with all the subgroups, and we could put these and set our file somewhere. You see we have some test ABC files. Set the frame range, subsampling if we need extra interpolation between those samples. You can export the actual particle system itself. You can export one single animated object per particle, or an entire object per group. If you use the particle system option, you can export different channels for those particle data as well. Let's see. Can I explain why the export node messes up the geo sometimes? I'm using TP 6.2 and have no lembic support, and it's a pain in the butt. I have a building crumbling cache, but if I export, all the geo goes crazy. Well, crazy geo is crazy geo is a descriptive term, and everybody knows that I really love pictures and files. So I would head over to the Facebook group and post that. Export, and what this person is talking about is here under operators export. And export has multiple options. You almost always want quality to be 90 or 100. And this controls how many keyframes are created over time, how finely. Excuse me. You will also want scale without size turned on almost all the time. And if you have changing topology, then what export will do is it will create visibility keys. So anytime a particle changes topology, it will create a max node with a visibility key that stops wherever that particle changed shape, and it will create a new object with a visibility key at 0 that ramps up. So really it's probably your visibility keys that are being a bit of a mess. So yeah, so next up from Rob Verduccia. Thank you, Joe. In creating the large scale effects in TP, how would you handle the scale? Does the team use real world scale, or is it a scale that looks good for the shot, or a mixture? Excellent question. Scene scale and production in a facility, my experience, and at my current place, Scanline, using a consistent scene scale as much as possible is best. There will be cases like in the Independence Day where things are so enormous and planet-wide scale that it's not possible to keep that existing scale. Most everyone knows, or they should know, that in 3ds Max, due to floating point and distance from the origin, if you look under your system units, lost it. Under your system units, the further you move away from the origin, your accuracy starts to decrease. So this is the floating point error margin that will happen. So yes, what we find is that in production, for the majority of shots, the majority of shots that involve humans, we typically work at a scale where the system unit is set to 1 unit equals 0.1 meters. So a human would be about, 1.7 units tall. So fairly small. Let me make sure I got all of that. And there are plenty of cases where, if you have a series of large shots, what we do is we go ahead and set up the scene scale to be, 1 to 100 or 1 to 1,000, whatever makes sense. Great question. Thanks, Rob. All right, so another question. If you change a single value, do you have to cache the entire sim again? Well, it depends which value you change. If you change things like dynamic properties, size, or anything that would affect the actual result of a dynamic simulation or any of the motion, then of course it's going to require that you resim. But if you are changing values that you can cache in a data channel and then modify post-cache, then you have the ability to modify those values post-cache and continue. The size example, there's a huge number of other other possibilities. You take a look at the, say for instance, the particle data and those inputs. Yeah, you can change the shape afterwards. So yeah, it really just depends what are you trying to affect. If it's anything that affects the motion, or that would affect a collision simulation, or a topology changing aspect, then yeah, you're gonna have to resim. Okay, another question. Was the scale for the latest Independence Day movie real world scale, all the buildings, or were they scaled to work with the tools to be more friendly? Yeah, same question as Rob, basically. Much like RealFlow and Maya, 1 unit, or at least the way we set it in Max, 1 unit equals 0.1 meters. And so, if you have a building that's 100 meters tall, yeah, 1 unit, so times 100 times your setting here, so you're gonna be 10 units tall. Yeah, unit scale is a tricky one. I'm still working on putting together some specific tests with things like the new flow operator, which have some scene scale or some built-in scale functions. But yeah, I still have to get around to those. Okay, next question. Is there some way to read time cached dynamics? This is from Max Rukadov. Yes, Max, you can retime cached dynamics. Let's actually take a quick look at that here in our existing cache. And what we're going to do is we'll just turn off this cache too. Oh, and duplicate our whole rule. No. TP, being the flexible system that it is, every dynamic set has a cache time input. And one of the things we can do is we can remap that. And so I could do it one way by saying, hey, take this float, pump it into this. You notice our max timeline goes from 0 to 240. Well, if I turn on animate and I say, hey, yeah, start at 0, at frame 50 I want to be at frame 50, but and then if I animate to say frame 200 and I only want this to be frames 80, and then I come all the way back to 240 and say go to 240, what this does is, let's turn off animate, our float value will be animated over time. And watch what happens to our existing cache. Our cache dynamic set, to be proper, let's reorder this, is going to look at the incoming value and set our cache time for whatever's cached to whatever's incoming. So right now we're at frame 34, it's roughly 39, and so you can see this slow down like this, and then it speeds way back up. So yeah, you can retime caches, do all kinds of bullet time stuff. It's not common, we don't do it a whole lot, but it can be done, And just because I say we or I don't do it doesn't mean anything, Go do it, go explore. Everybody I work with knows that that's the mantra, Go find out, push it to its limit, see what it can do, see where it breaks, and we'll deal with it then. One of the important things, if you are going to retime stuff, what you'll want to do is you'll want to change your master dynamic samples. I would recommend about 120 samples per second, because that will allow you a better smoothing between keyframes that are set here in this cache. Unfortunately, the cache, last time I checked, does not interpolate between frames. What it does is it steps through values. So whatever is coming in, it's going to step to the closest value. Alright, so let's take a look. What's next? Next question. from Cloud Effects. Please give me some tips on how to minimize fragment interpenetration when using VB and prefragged objects. Sure thing. All right, so prefragging and fragmented objects in general. Let's I'd kind of like to bust something out, but let's do this. Let's go ahead and take this object. Let's put it in the red group. Use its shape. Let's go ahead and take that red group, put it in a volume breaker. Volume breaker. And let's set volume breaker to put those into the blue group. Activate 100%. And let's just go ahead and see what we get. Let's go ahead and hide our source object. Let's, yeah, we got this. Okay, so let's actually set volume breaker to only activate 50%, so it keeps them. And you can see that our volume breaker raster is too low. So if you really want to keep objects from interpenetrating, especially when doing collision simulations, a really handy trick, actually let's set this to be top down or Z-neg, Z positive. Oh no, Z-neg, that's right. Yeah, I'm looking for, I want blue. So a really handy trick is any fragments or any objects who are going to go into a shape collision or bullet sim or any kind of dynamics, scale it down a little bit, you know. Hey, what happened? This is how you know we're live. Things go wrong. Okay, so you see, you get a little bit of a gap in there. And actually a really funny thing is, during a show, we found out that right around 97 to 96% of a scale gap, people will notice that the scale has changed. So, you know, probably best to keep it at like 98. And so when things fragment, it has a little bit of space in between them. The other good thing that you can do, and what this person is talking about, is if they have, you know, an SC sim or a bullet sim. These are the solvers for collision engines. If you have these, in SC, you can set the collision and contact iterations higher. In bullet, you can set the physics iterations higher. But what really matters most is on the master dynamic. So set your samples per second higher. And unfortunately, what this is going to mean is you're going to get a bigger cache, but you know what? Big deal. A bigger cache, you get a better result. I'll take the better result. Let's see, what's next? Okay, so someone asked if I plan to come out with a comprehensive TP6 training. Short answer, no. I will come out with some new videos for TP6, probably in around spring of 2017, but not a comprehensive. There are so many videos right now about thinking particles by so many great artists that they really cover a huge portion of what can be done and how to do it. There are, of course, all other ways to explore, but no, we're very busy on 3 projects right now. We're trying to wrap those up, and then, but yeah, there are some new features and some new methods in TP that I think will be very helpful. The other cool thing is that the versions of TP, ever since version 4, when Goran and I made the Thinking Particles 4 for production, 1.0, the logic that's in there, 90% of it still holds true today, or maybe 85. There's some new improvements. You know, there's the new value to value, which is amazing. But everything that's in the TP4 videos and TP5 videos is still very relevant. So definitely check all those out. You know, there's 27 hours of videos that me and Goran made. So see if you can get through that. All right, next question. When TP caches a complex scene, some original material is lost using TP 6.4 SP1. How to resolve this? This is a very good question. And what we do in production, I will show you what we do. Let's go ahead and we'll keep that system. We'll create a secondary system called production shot. And inside production shot, we'll create some more groups. You know, maybe we've got structures. So here we've got house. Let's make another group under structure. Let's call this building. And so we've got all these. Let's put these under here. You know, let's say we cache our production shot. But something that very important that we want to do, and this goes, this is an important concept. If you bring in multiple objects who have different materials, there are different ways of dealing with those materials in TP. When you create a cache with TP, like this one here, let's go ahead and explore this directory. When you create a cache locally, it creates an MAT file. And this MAT file stores a material structure for the TP and all the objects that were brought into TP. And so your MAT file is there and it's intact. Let me see if I can actually drop this in there. No, I didn't want to do that. But you can open this guy. So here's, this is our cache material tree. This is what's inside our MAT. It's really just thinking in a single material. Not very exciting because there weren't a lot of objects brought in. If you cache locally, you can keep your MAT and you can render with it. That'll be no problem. If you are dealing with caching on the farm, Max unfortunately has a restriction where it won't save an MAT file. And so a very common approach is to, we cache this cache production here, and we'll, set up something called a material override. And inside this material override, you can then say, well, for the house, I want to assign a shape material here, and you go ahead and you pick whatever material was on your asset, drop it here. And if I have a building, and then I take the building, I pick the building material from the scene, and then I instance that here. And so now, after the cache, my particle groups are going to read the cache data, and then they apply a new rule that applies those materials to those groups, and this will restore those materials on there. Let's see here. Next question from Oslansi. I'm wondering about how one can manage to get particles to follow a surface without using surface follow. Been driving me nuts for a while. Yeah, right? So, like most things in TP, there's probably multiple ways to do this. Depends if you are talking about, let's go ahead and create a plane object. And then let's animate this plane. Let's set a keyframe here, another keyframe here. Let's set a bend modifier. And we'll set a keyframe for the bend and up to here where we bend. Oh, not the angle. Let's try that again. Direction. You can tell I use the bend modifier a lot. Oh man. Well, there we go. Okay, I just had the wrong axis. Let's delete that and try again. Let's go, no angle, a little bit of direction, bring it up here, let's add, okay, more direction, and here. And let's give our plane some more resolution. Too much resolution. So in order to have this particle, have particles follow over this surface, let's go ahead. I do have some black boxes. Let's get a generator birth node surface. This is somebody on the Facebook wanted to know about how to use timer stuff as well. Unfortunately, that's a whole topic in itself, but I can tell you that if you connect a Boolean true into an egg timer set to single and zero, this will just this is handy because it'll fire once when the sim begins. So this is a trick we use quite a bit. You fire this into a position borns, put them on the red group, and we'll pick the node of this, and we'll go ahead and now. Let's see, how many particles do we have? 1. Let's try 1,000. Try that again. Okay, so there's our 1,000 particles. Well, trying to get stuff to stick onto a surface, there's different ways to do it. You know, I have something here called a surface tracker. It's a whole black box system because we do this quite a bit, where you pull in geo. In this case, what we're doing is we're storing the face ID, and then there's this crazy function where you can say, hey, I want the particles who are tracking the surface to look up that face ID on the geom face, and we take these, we get the vertex IDs for that face, and we basically calculate the normal of the face, but then we take those, we take the positions of the verts, create 2 vectors, and this is a very handy script operator we wrote called 2vec alignment, which I think we will release soon if it's not already out there. And this will, what this does is it creates and allows particles to know where the verts are on the surface and properly align themselves even during deformation, so that there's no flipping when the surface goes over. Now this is a very complex example, right? So there's different ways to do it. You can, we could take our surface position, maybe take some UV coordinates, store those into memory, and you know, UVW is going to be a vector, so store this into here. Dump surface tracker, say, hey, red, read your memory. And what do we want to do? We're going to have to look up that surface again. So let's go ahead and take this data. And there's different ways to structure this too. A lot of my awesome coworkers like to pull all the nodes way up higher so that you only have to access them once. That's a good technique. We could say, hey, get this, read this UVW, output it back into here, look it up, and then set my data again. Nope, not alignment, not that. Okay. So question next is, do I plan to do another tutorial using actual models like live action for film? The answer is yes. Unfortunately, like I said, we're in the middle of working on actually 4 films. Those will mostly be done in spring and next summer, but I think maybe by spring we should have kind of a high-end destruction tutorial online. So yeah, there'll be more news about that when it happens. Okay, so another question, can Fume and Phoenix bind with TP? I'm pretty sure this person means can they talk together and share data and use each other. I'll give you the short answer on Phoenix. Yes, but I don't know how much. It's been a long time since I've used Phoenix. Can fume? Yes, definitely, and pretty well. There's really close integration between fume and TP, both with particle emission, data channels, TP shapes, etc. So yeah, it's very powerful stuff. I created a system. Somebody's asking about this noise turbulence system in TP, and it's probably the 3D noise field, and of course it was created with a beta version. But what this does is, and this is part of one of the beauties of TP, is using a dynamic set where you can restructure things, or so you can have your own custom inputs based on whatever you wire to this dynamic set input, which is right here, or right here, the output. And so this 3D noise field, you can use texture maps, which gives you the ability to modify their size and whatnot, phase, etc., and refeed this color value, which is the 0 to 1, black to white value, and in order to create a vector field. And there were some folks on Facebook who had really great examples of these things and how they moved. We actually just recently used some of that same method in shots for Power Rangers. It's pretty cool stuff. But short answer, no, probably not going to touch this up. I will say that there is, and I'm sorry, I don't know if I have it here, but there's also cool things where you can modify and drive the texture behavior from inside TP. So you don't always have to go into the material editor. Let's just show a quick example of how you can do that. Let's create a map. Let's create a, say a smoke. We're going to set this to world XYZ. And then TP has a very handy standard operator called paramblock. And paramblock allows us to pick an object in the scene and access data about it. In order to do this, we create a sphere, apply this material to the sphere. We come into paramblock, pick this, and now you see we've got the geosphere. We have the material as well, and here we have the map, and we have things like size. We can make an input, phase, make an input. So what we can do is we can control these same texture maps that are in this 3D noise field by applying these same textures to objects in the scene, connecting those with the paramblock. And then we can do things like, we missed phase. There's phase. So then we can do things like control these over time. Now controlling them over time is an interesting technique where I'll show you this. There's a black box. We use black boxes all the time. You make one piece of logic and just use it over and over. It's so handy. I've got something called time and frames. And I don't want to get your folks' hopes up, but I'm going to release a bunch of these black boxes also by spring, so hang in there. So this is a float that has a controller that reads the actual scene frame rate. We convert this into frames, and then we can say, okay, so the frame coming out, we can use the value to value, and we can say, well, and my frame range goes from 0 to 100, and I'll give you guys a big hint. Most of our shot work happens from 1001 all the way up to whatever. Let's set this back to film. So let's take, now we can say, okay, so if I know on frame 1010 up to frame 1100, 1100, I want to modify my size from whatever it is right now, which is 10, and I want to make it 5 times bigger. I can wire this up, and so now this texture will be driven and controlled by TP. Actually, let's show this. So you can see this thing getting bigger up here. And because TP is actually controlling the texture itself. And so this is pretty handy. You tap this into the 3D noise field, and then you can do, modify it as you go. Phase is another great one. You want to have this texture evolve over time because you don't want your 3D noise field to always be static. That's another great way. Let's see here. I'm sure I probably missed somebody in the chat. I'm sorry, but let me jump in and... Boom, boom, boom. Paul Harrison. Sorry, man, I missed you earlier. Question about the data channel setup. I store the size and modify it. Could I also modify the size without storing the data channel? Definitely. Yeah. Once you have particles inside of a cache, you can then put that, and we'll call this cache 1, and this will be cache 2. If cache 1's already cached, you can apply rules in the next dynamic set that will affect those same particles who are in cache 1. Yeah, we do that all the time. Mingwei Li asks, so many people say Houdini is better than TP. Can I give some opinion? I go back to something I said earlier where it's kind of like your preference. If you start with Houdini and you learn it really deep and you enjoy it, then by all means, use whatever works for you. Thinking Particles is very flexible and fast. It's not entirely procedural, so it allows you to kind of break some of the proceduralism, which can be very handy sometimes if you have to hack things together or make drastic changes very quickly. One of my excellent coworkers once said that in TP you can, the first 80% you can go really fast and pretty easy, and it's the last 20% that's kind of challenging as you have the system and then you try to make changes to accommodate whatever the supervisors and directors are asking for. And this person went on to learn Houdini, and they came back and told me that, well, yeah, in Houdini it seems like we spend the first 20%, we spend the most time on the first 20%, and then the rest of the 80% is kind of the easier time. So it kind of depends, I think, how you like to work. So any tips for building controls into setups? Yes, be careful. No, there's a lot of ways to build controls into setups. Some people like to do things where they build multiple layers up, and so they will set up all their controls kind of up at a top level. Let's do this. Where I'll have, let's take my phase as well. Phase, let's put surface position. So you get things like this where I have all my controls kind of built up here at the very top. This is kind of handy because it allows you to do all your modifying of main values in one place up at the very top. But there's a drawback, and some people may not agree, which is totally fine because there's a million different ways to do things in TP. But having to maintain controls and wires between dynamic sets at a certain point will become kind of difficult or messy, where you're always having to go back and wire things. So what I actually recommend doing is very handy technique where, you build, if you've seen some of the videos, you know that we call this like mem master or mem key, the main value. And then what we'll do is we will create different variables, and then we'll go ahead and store those variables here. And then now everything's going into memory. And this way with memory, we can then, we come into here, we could say, well, access my memory, give me any of those variables, and just feed, whatever I want, wherever I need it. And then, of course, I can come into this, I can paste this guy in, then I can access other parts and just feed other parts in here. Using the memory is very flexible. The thing that everyone needs to remember, there's two things about memory. The first one is that memory values are not cached. So if you need to cache any data, use a data channel. References are not cached, so do not use those and expect them to be in your cache afterward. Data channel is your only, I'm pretty sure, it's your only way to cache extra data to particles as variables. And the cool thing about data channel is you can store, you can store a value per sample per particle. So every particle has its own value over time. There's some other pitfalls that you have to watch out for. If you have already cached values into data channels and you cache that, and you're trying to read and modify those data channels, you have to remember to do that, modify that data channel every frame or every sample afterward. Otherwise it'll only be set once and then it reverts back to the cache value. So yeah, a little bit dangerous. Let's see here. Someone asks, what do I look at when we receive a demo reel? What to avoid putting on it? Well, let's start with what do you want to put on a demo reel? You want to put your best work first. I personally don't mind, and I actually like demo reels that are, 4 or 5 minutes long. Put a wide variety of work. Show the different skills you have. Show your flexibility. Definitely indicate what you did on the shot. These Independence Day and a lot of the scanline stuff, there's hundreds of people working on those. So definitely be clear about what you did. Don't never take credit for somebody else's work. It's a big no-no in VFX, and people remember when people do that, so be careful. You can put tests and, just cool looking tests. If it's a simple test, not so excited to see it. If you're doing an online class and everyone is making the same same sample, when we see those, it's like, well, yeah, it looks pretty much like everybody else's. So kind of what we want to see is we want to see something that looks unique, and something that looks like it came out of a movie. So take your video camera, go do some filming, do your own match move, track a shot, and make some cool effects for it. Let's see what else we have. From my good buddy Kei Yoneoka. What's up, Kei? Kei, you had a great breakdown. Your studio is doing so well in Japan. Congratulations. So his question is about deforming the window frames using the soft body approach in Independence Day. There was that one building that comes down where it looks like it's deformed. Honestly, I don't think it is. I think what happens there is there are enough subdivisions in volume breaker that it kind of blends and looks like curvature. So one way that you can do deformation, though, of course, you probably know this already, is you can use particle skinner. You can create a PRT using TP particles, export that PRT, and then have that PRT use particle skinner and the high-res geo in order to deform the high-res geomesh. Very powerful technique. Like I said, I'm very hopeful that Cebas will consider the possibility of including some deformation methods inside TP where particles and particle shapes can affect and deform other particle shapes. Very similar to a skin wrap. Yeah, the logistics might be difficult, but I'm pretty sure it can be done. All right, next question is, do I personally like SC or bullet physics? Bullet physics or both equally? This comes from Walker. Walker, I will be honest. SC and many of my fellow artists at work and all of my former co-workers know that SC is an extremely accurate and precise collision engine. It offers some of the best collisions I've seen, and the bullet physics is very fast. In some cases, it can be up to 6 times faster than SC. And so when your sim takes an hour in bullet or 6 hours in SC, it's very tempting to use bullet. You just have to be very careful with the settings in bullet. The version, and bullet it's open source, and there's other different implementations out there. This version that's in TP6, I don't know the exact version number, but of course the bullet development continues, and so Cebas has to continue to invest and update this to keep it current and add features. And this is why investing in your tools is really so important. Cebas has to pay programmers to implement these features, and they need money to drive that development. And unfortunately, in the world, there's a lot of software piracy still, and so it's very important to support the software that you use on a daily basis, and to really put your money where your mouth is. And if you're making money off software, you should definitely buy it. There's no question. So